Just giving it a few seconds just to allow people to join the webinar. So just bear with us while that's happening. And I think we'll make a start now. Good morning, everyone. You're very welcome to this morning's State of the Science webinar, which is being run by the New Zealand Agricultural Greenhouse Gas Research Centre. My name is Sinead. I'm the current Acting Deputy Director here at the Centre based in Palmerston North. And we're really lucky this morning in that we are joined by Dr. Jeremy Hill, who is the Chief Science and Technology Officer from Fonterra. Jeremy, of course, comes with a wealth of knowledge around the ag sector, both globally and here in New Zealand. And I think we're really lucky to have Jeremy here this morning to help chair the session. We've also got two fantastic speakers lined up. So I'm sure you don't want to be listening to me. So I'm going to hand over to you. Jeremy, over to you.
Thank you, Sinead. Hey, welcome to this webinar series from the AgResearch. We're really excited about this one, and I'm sure, like me, everybody on the call is really keen to learn about the potential of breeding for low emissions cows. And we've got a great lineup that's going to help us through that process. So we've got Lorna McNaughton, who's a scientist with Livestock Improvement Corporation, and Suzanne Rowe, who's a senior scientist with AgResearch. Just a couple of seconds on how we're going to approach this. Each of our presenters is going to have around 20 minutes to take you through a presentation. At the end of that, both presentations will then have questions. Could you please type your questions in the Q&A? We'll try and get through as many of those questions in the time we have for this webinar. And then over the next few days, we'll try and answer all of those questions that we were not able to get through, and those will then go up on the website. So give us a few days to do that. I've been through a few of these where we've had a lot of questions that we've needed to work through. So if I can start with Lorna. And Lorna, I see that you have been working on trying to determine how bulls emit methane, and I did see that you did some work on collecting methane from bulls as part of this particular process. And I'm keen to work out which is actually more dangerous, semen collection or methane collection. I'm really excited about what you're going to tell us this morning, and please begin your presentation.
Thank you, Jeremy. And I'm pleased to say that for me, it's a lot easier collecting methane than being in with the bulls and trying to collect the semen. It's a much more automated process that we've come up with. So we are very much at the beginning of our journey in terms of breeding for low methane. So I'm going to tell you about kind of how we've gone about the process and where we are now, and share just some preliminary results from the work we did last year. And I'd just like to say that this is a joint project between LIC and CRV. So I work closely with Phil Beatson, who's Head of Research at CRV on this project. So just to quickly cover the why. So we know that methane is a potent greenhouse gas, and with the zero carbon bill coming into effect, we need to reduce methane by 10% by 2030 and by up to 47% by 2050. That exact figure will be altered depending on what technology we find and what the political landscape looks like at the time. We also know that there's unlikely to be a single silver bullet that's going to fix our methane issue. So we need to take a multifactorial approach and make gains where we can. And we believe that breeding is one of those areas that can contribute. It's unlikely we can contribute much in the breeding space in cattle by 2030, but by 2050, we could be making a reasonable contribution. So briefly, what are some of the reduction options for methane? I'm not going to talk in depth about these. We have got a lot more efficient in terms of how much product we produce per kilogram of greenhouse gas emissions. and there's more work we can do in this area. We also know that different diets can have an impact on methane production, but a really important point to note is when animals are fed the same diet, if they eat more, they produce more methane. So there's a very strong relationship between intake and how much methane is produced. Methane inhibitors are also looking promising, and it'll be interesting to see when those get regulated for approval. I'm not going to mention about vaccines, that's not my area of expertise, but there's some potential there. And then genetic selection, so my particular area of interest. The nice thing about genetics is it's permanent and cumulative. So we don't expect to be making massive gains per year in genetic selection. It might be 0.5 or 1% per year, but that all adds up and accumulates over time. So over a 20-year horizon, we could be making quite a substantial impact on our methane. So how do we do genetic evaluation and selection? When we're looking at genetics, what we're trying to understand is what is the component of the animal performance that we see that is down to genetics and what's down to the environment. So our genetic evaluation is basically doing this. We need lots and lots of data to do this because there's obviously lots of things that can impact an animal's performance. And this is thinking in terms of the broader environment, right from conception through to how the animal's treated in the herd. And when we think about genetics, it's not just a single trait. So traits like milk production are correlated with other traits. So for a long time in dairy, we selected almost solely on milk production. But what they didn't realize at the time was that milk production was negatively correlated with fertility. So we ended up with cows that were a whole lot less fertile. Now most countries in the world include factors like fertility and animal health in their indexes. So we need to understand how the traits are related to each other when we do the selection, and that's going to be really important for us to gather that data for methane. So can methane be selected for? The good news is there is genetic variation, and Suzanne will cover a lot more on this in the sheep work they've done. And there has been some work in cattle showing there is genetic variation. The Danish and the Norwegians are doing quite a lot in this space, and the Australians have done a little bit as well. But it isn't an easy to measure trait. So ideally we'd get 1,000 to 2,000 phenotypes, and that's basically just a measurement of an animal before we can get some reliable data. But it's expensive to get each of those measurements. So lots of the countries around the world might have 500 measurements, but they haven't really got that big data set yet. It's also hard to measure in grazing milking cows. So really we want to know how much the animals are eating when we measure the methane, and that's really hard to do at pasture. We might be able to estimate how much the herd is consuming, but at an individual animal level, with a high level of precision, we just haven't got the technology to do that without putting animals in a barn. And the other thing is, traditionally in dairy, we look at the performance of the daughters of a bull to figure out how good that bull is, because clearly bulls don't produce milk. But methane's actually a trait that bulls do have. So bulls produce methane, just like cows. So this is something that we could potentially measure on our bulls. And so we've decided that bulls will be the animals that we try and measure, because between LIC and CRV, our bulls are siring around 90% of the dairy cows in New Zealand. And our high-use bulls will be generating 10 to 30,000 daughters or more in a single season. So the genetics can be quickly disseminated. So we've selected to measure bulls, but then the question was, how are we going to measure it on this number of animals? So technically, from a precision point of view, the most accurate way to measure your animals is to put a single animal in a chamber and measure all the gases that go in and all the gases that come out. But It's really expensive. The animals don't particularly like it, and you really can't leave the animals in there for very long, and they don't display natural behaviour. So while it's good for small studies where you need a high level of precision, this just isn't a practical option. And there's only a handful of these facilities in New Zealand. So the sulfur hexafluoride technique is something we've used in the past when we tried to do some work on cows quite a number of years ago now. So these animals in the picture here have got little canisters on their back, and they've got a halter on the front with a little pipe that sticks down to capture a sample of their breath. They've got a little capsule in their rumen that's releasing sulfur hexafluoride at a known rate, and then you analyse the canister on their back and work out the flow rate of sulfur hexafluoride and work out how much methane they're producing. The technique works, but it's quite technically challenging, and there's a few little things that can go wrong along the way, and we didn't feel like this was a great fit for putting on our bulls, particularly if we're putting it on bulls in a shed where they could be jumping on each other and playing and fighting. There's also methane sniffers. So these are more commonly used in milking robots. So the cow will go and get milked. Typically they'll mount a sniffer above the feed bin where she gets some concentrate feed, and they'll measure the cow at milking time. So that works well in indoor systems where the cows can have their intake measured and they wander along to the robot and they can get measured for methane. There's a few challenges for getting precise measurements from an individual cow in terms of how close she puts her head to the sniffer. That can have quite a big impact on the methane measurements. And there's also handheld lasers, but again, they are not precise enough for individual cow measurements. They might be suitable at a herd level, but not for what we need to do for genetics. So where we have got to is to use the green feed system. So this was developed by the Zimmerman family in South Dakota, and Tom Zimmerman was the man who brought the sulfur hexafluoride system over to New Zealand. We need to use the green feed. We need to entice the animal to put their head into the hood. And you can see on the picture there, there's a feed bin labelled, and that's how we get the animals to put their head in to measure their breath samples. So we can program how much feed they get. Each feed drop is about 40 grams, and you can program how long between drops. So for cows, you might drop at 30-second intervals, whereas our slightly smaller yearling bulls will drop at a 45-second interval. And we want to drop enough feed to hold them with their head in for 2 to 4 minutes to capture at least one methane release cycle. So the cows typically will burp every 1.5 to 2 minutes. And if we can hold them in there for at least that long, then we should capture at least one burping event while they're in there. So the system works by having a fan in the chimney, and that creates airflow, which makes sure that all the cow's breath is sucked up the chimney and their little subsamples are taken and measured for methane and CO2. And it gets around some of the problems around head position by having a sensor in there. So only when the cow's head is in the right position will the data be transformed into useful methane data. So we'd figured out how we'd measure the methane, but then the other thing is, what are we going to feed these animals and where are we going to put them? So if we want to measure intake, we really do need to be housing the animals. So we decided we'd be putting them in a barn, but we wanted to make sure we were feeding them some kind of a forage, because New Zealand dairy cows, most of their diet is grass. It's a forage. We don't want to be doing our selection on a concentrate-based feed and introducing those kind of unknown variables into the mix. So luckily, Dairy NZ and LIC had previously done some work on feed conversion efficiency and had sought out a kind of suitable forage that could be fed to animals indoors. And they'd selected on lucerne cubes, which you can see pictured there. So they're cubed lucerne hay. Unfortunately, we don't produce these in New Zealand, so they have to come in from overseas. The advantage of these is they're very high dry matter, so about 90% dry matter, and we can get away with feeding our bulls once a day with these, whereas if we're trying to feed silage or something similar, we'd be having to feed multiple times a day, and it would be very hard to get the consistency between batches, because for our genetic evaluations, we really want consistency between runs and also as consistent as possible between years.
Lorna, you're about halfway through time-wise. I'm going to have to be reasonably strict. You're okay, but just,
yep.
Thank you.
Perfect. So we'd come up with our plan. So then the idea was to test out our plan for the pilot trial, because you don't want to roll into a 300 animal trial not having ironed out all the teething problems. So this is our barn being built at LIC. So CRV luckily had barns built already, and we were able to copy their design and modify it a bit to be more purpose-built for methane. So we got bulls finally into the pen last May after lockdown. We'd been just about to put them in when we got shut down last year. So this is the back view of the pen. So you can see top left are the 2 feed intake bins. We weren't quite sure which type of bin we were going to buy at that stage, but we've gone with the one on the right. And in the top right-hand side is the green feed methane measuring machine. So this was just before the bulls were in, the engineers putting the final touches to the pen. And it's a 6 by 9 metre pen, and we put 12 bulls in there. So these are yearling bulls, kind of 9 months old. So anywhere between 150 and 300 kilos for most of the bulls. These ones were more like around 200. And this is the bulls in the pen. They really quickly learn how to get to the feed. So we've exposed them to the feed in the paddock, so they know what they're after. And you can see there's a bull visiting the green feed machine in the far left of this picture, and the others are either chilling out or chowing into some feed. So that's a single pen. When we run our full trial, the aim is that we'll have 8 of these pens. And then once we'd done our testing at LIC and learned a few things of what we should and shouldn't do, then we moved over to CRV. So their pen setup is slightly different because they have existing infrastructure in the central raceway. We've got the equipment actually in the pen with the bulls. So the methane measuring machine is on the left and the feed intake bin on the right. And for that reason, we've only got 8 bulls in a pen here because there's just that bit less room. And you can see here, this is a grab from video. So all our pens are videoed 24/7, and it's a great resource for when we have kind of any questions. We've got some slightly funny looking data. We can go back and look at exactly what was happening in the pen at the time and resolve if it was 2 bulls trying to push to get into the feed, or kind of what we need to do to fix that for next time. So it's great. Video cameras are so cheap now. And this is probably what you've all been waiting for, some actual methane data. So this is the raw data from the machine. It's 2 hours worth of data. The red line is the methane and the blue line is carbon dioxide. So in general, when you get methane emissions, you also get carbon dioxide emissions because it's in the animal's breath. So it's obviously a chunk of carbon dioxide there as well. And when you haven't got a burp event going on, you can get carbon dioxide without the methane. So you can see a little couple of blue spikes there without a spike in the red line. So this is absolute raw data. It then gets transformed into grams of methane per animal per day. And that's what we use for our analysis. So this is the methane grams per day for the 8 bulls we had in our CRV leg of the trial. So you can see there's some differences between the bulls, which is good. And you can see there's quite a lot of day-to-day variation. Now, some of that was one day the feeder ran out and there was a little delay in picking it up. So there was a reduced intake one day and a bigger intake the next. So that's been a good learning to make sure that doesn't happen for our main trial. But the phenotype we're most interested in is actually thinking about methane per kilogram of dry matter, because the risk of selecting for just methane without thinking about how much the animal is eating is that we could select for animals that just have a low intake. And with dairy cows, we're trying to get them to eat as much as possible so they can make as much milk as possible. So we don't want to be selecting for that. So when we worked out how much the bulls were eating and applied that to the methane, it was good to see that the data was around what we expected. So the national inventory is around 21.6 grams of methane per kilogram of dry matter, and we were in that ballpark, and we saw some variation between the bulls. So we only had 8 bulls. We can't do any genetics work with those small numbers, but it was encouraging enough for us to want to go to the full trial. So this is my last slide. So what's our timeline look like? This year, we hope to measure 300 bulls, which would be all the bulls in CRV and LIC's progeny test scheme. And these bulls would then be used in dairy herds this spring. They would have some progeny born next year. I would like to do some testing, perhaps on the progeny of some of the extreme high and low bulls, and Suzanne will talk more about some of our ideas around whether we can do a calf pack chamber. And then those progeny will be lactating in 2024, and our final test is really to see if the daughters of bulls that are high and low for methane are actually high and low for methane when they're lactating. So by then, hopefully, if all goes well, then we should have some low methane semen to sell in 2025. But there's a lot to know along the way and a lot of genetic correlations and things to find out. And I hope that maybe not us, but the likes of Dairy NZ and AgResearch can use some of what we find to try and understand why the differences exist. So thank you. And thanks to NZAGRC, because they are funding this work, the Bull Farm staff who help us look after the animals, and Gemma, Peter and Gary, who have all been invaluable to getting to where we are now.
Thank you, Lorna. I'm sure there are, in fact, I know there are some questions because we've already got some. We'll come back to those in around about 20 minutes time. We're going to roll straight into Suzanne's presentation. Suzanne is the co-leader of the AgRC, PGGRC program to develop low emissions ruminants. That's had quite a degree of success with sheep. And today we're going to hear about how those learnings can be transferred to their big sisters. So I'm looking forward to hearing this presentation and the potential. So over to you, Suzanne. Thank you.
Thanks, Jeremy. Yeah, so I'm going to talk about breeding low-emitting ruminants. No, frozen, sorry. I'm going to stop sharing and reshare. Let's try that again. I'm maybe just chatting away. Give me a second. Aha, okay. I'm hoping my slides are changing. Jeremy, can you confirm?
Yes, you're changing.
Perfect.
You're all
Perfect.
good.
Okay, the joys of Zoom. So I'm going to talk about the technologies that we've developed in sheep, but I'm going to particularly focus on the ones that transfer to the cattle industry or have potential to transfer to the cattle industry, and how we might use the learnings from. We've had the luxury a 10-year research program in sheep. So we're not galloping quite as fast as Lorna is. We have the benefits of hindsight and large numbers. So really hoping that some of the learnings that we have can be applied straight into the cattle sector. And the whole sort of premise is based on, as I've said, a 10 or probably a 12-year program now, which took thousands of sheep, monitored them through varying protocols, and developed high and low methane selection lines. So we have 2 flocks of sheep at AgResearch, supported by the NZAGRC, one of which has been bred solely for high methane for the last 3 generations, and one solely for low methane. And they've been monitored for all other characteristics, but not been selected for anything but methane. So we have this really great resource. So I'm actually going to start at the end. I'm going to start with where we've got to in sheep. So we have research flocks, we have the selection lines that I've just described, but we also have other research flocks where methane is a phenotype, and it's part of the profitability index that we use to select rams. And the selection line animals have had detailed respiration chamber measures. So those measures are very accurate. They've given us absolute methane measures. So they've told us exactly what these sheep are producing per day. And we've measured those in 6-minute intervals over 48 hours at a time. So that's given us a really clear picture of what happens in the sheep. We've been able to look at the variation, the diurnal variation, so daily variation, what happens when we feed an animal, and basically really draw some conclusions on what we can do to measure sheep in larger numbers. And we've moved to what Lorna referred to as pack chambers. And these are portable accumulation chambers, is what PAC stands for. And it's basically an 800-litre sealed unit where a sheep is placed in for a single hour. There's a valve on top of it, and we use a device that you would take down a mine, and it draws off a sample which monitors the methane, the oxygen, and the carbon dioxide that's being given off in that hour. And given what we know about respiration chamber measures, what we do is wait until 1 hour after feeding, because data tends to be noisy around feeding. And we've been so far measuring animals twice, 2 weeks apart. And that gives us a really clear picture of how the animals rank. So we've obviously validated back to the respiration chambers. And what we don't get from a pack chamber is the absolute emissions. We get a lower figure, but the animals rank in the same way as they would in a respiration chamber. So it's a very low cost, high throughput tool for ranking animals for breeding. And at the moment we measure on farm anywhere between 80 to 100 animals per day, and the cost per measure is $30. So we've gone from spending about $1,000 a measure in a respiration chamber to having thousands of animals measured on an annual basis, and measuring those thousands of animals has enabled us to get the genetic correlations with the production, the productivity, and the health traits that we measure in the sheep. So what we now have is the metrics and the ability to be able to put this into a selection scheme and know that if we select for methane, what the impact we will have on the other traits. So we can model that going forward. And the final sort of part of the picture was to take this out on farm. Now on farm, we're not going to put every single animal through a pack chamber. That would be untenable, even at the rate that we can measure. So on farm, what we do is we go to a breeder, and we would measure around 15% of the animals that they want to evaluate for their rams. And we would try and take sort of the top and the bottom. You know, we really want to know what the variation is on the farm. And the remainder of the animals will have a genomic profile. And what that leads to for the breeder is this is in conjunction with Beef and Lamb New Zealand. They've set up breeding values and a module. PGGRC are supporting this. And when we go to a breeder, what they end up with is a list of their animals or their rams with a breeding value that tells them how that animal relates to the average animal in its flock, and how it ranks. And what they can do then is perhaps choose from their top animals, if they have an animal that has a similar profitability index to another but a much higher methane breeding value, they can opt which one to select, and that's really what it's being used for at the moment. Once we have a value for methane, or we understand how this data might be used, things will probably change slightly. So it may be that it goes into the breeding worth index as a sort of overall profitability. We currently, within our own index, a gram less methane per day, we value at about $6. But that will change depending on how the government decide to value carbon, and whether this is indeed just something that goes into your environmental plan. So that's the state of play in the sheep industry, and that's where we'd really like to see that the cattle industry get to, where they have tools that they can actually select bulls. So whilst this has been going on, we're still really trying to push the envelope with the selection line sheep that I talked about in the first place. So we're 3 generations in, and we're really trying to take really detailed measures of those animals and all their progeny. So that's things like feed intake, feed efficiency. We're profiling the microbes in their gut. We're looking at slaughter data from their progeny, and we're actually looking at the physiology of the animal. So we're CT scanning, and when we slaughter, we're taking the alimentary tract and having detailed assessments. And this is where we got to. This is what we know about the low methane animal, given our experience, and we have around 5,000 measures. So after 3 generations, we have 11% less methane per kilo feed eaten on average. There's a big variation, but the average is 11%. The low line has 20% smaller rumens than the high line, and that happened very quickly. Probably most of that change was in the first generation, but they do have the same surface area. So the rumens have longer, denser papillae. So we've seen a physiological adaptation. When we look at feed behavior and feed efficiency, we see that the low animals actually eat slightly more, but they eat little and often. When we profile the microbes in the gut, we see that there's a very different microbial fermentation. It's a very, very strong signal. It's very straightforward to take a profile from that flock and say whether it's a high or a low. So we can predict the methane status based on the microbes, sequencing the microbes in the gut. Leading on from that, when we look at the outflow from the rumens, so there's a fermentation process, and there are volatile fatty acids being produced that are energy precursors for the animal. We see changes in that energy profile. We see more propionate in the low line. We see less acetate, and that's borne out actually in the animal itself and in the physiology. So we see more lean growth associated with the propionate. We see less fat in the low lines. They have less acetate. We actually see more wool. But the most important thing is that we've been selecting purely on methane for a long time, and we have healthy and profitable sheep. The low line actually has a higher gross margin than the high line at the moment. So we're relatively comfortable that the changes that we have made have done no harm. So moving forward, what we really want to know is we have direct measures of methane, but are there indirect measures? Are there ways that we can continue to monitor large numbers of animals, thousands of animals, in fact, in a sort of high throughput way that's informative? And one of the most informative phenotypes that we've taken to date is this rumen microbial profile. And this is an oral tube. So we put a tube into the rumen of the animal. She swallows it. We draw with a syringe. It's a very simple method, about 20 mils of rumen fluid. That rumen fluid so far has been freeze-dried, ground, DNA is extracted. It goes through a sequencing protocol, and finally we have a microbial community for each animal, and we use various sort of statistical ways to sum that microbial community to compare one animal with another, and we're seeing heritable variation in those microbes, so beyond what we feed for. And when we actually use those differences between individuals, and we try to predict traits such as feed efficiency or methane, what we see is that, so here we've got a bar graph. The G, so the blue bars, that's a cohort of 3,000 animals where we predicted these traits using genomics And the orange bar is where we predicted these traits using only the microbial profile, and the grey bar is when we joined all the data together. So what we're seeing here is that if we use microbes and the animal genomic profile together, we get a more accurate picture of feed efficiency and methane emissions and methane yield. So that's a really exciting thing to take forward, because it's a very straightforward way of sampling really what's at the crux of the matter. And we've gone a bit further with this. So we have a couple of research programs, and as I've said, what we're really interested in is an assay that basically we can use for many thousands of animals. And rather than restrict ourselves with a microbial profile that only uses microbes that we can identify, in other words, microbes that we know are there, we've gone for a reference-free approach, and that's where we sequence everything, and we have microbes that have never been cultured. We don't know what they are, but we know that animals share them, that they carry them. So we're using a reference-free pipeline. We're really not interested in what the microbes are or even what they do. All we're interested in is which animals carry them, which don't, and whether that predicts their methane or their feed efficiency status. So we've gone to the reference-free bioinformatic pipeline, and on top of that, we've tested ways of handling the fluid. And we're now at the stage where we can take a 1 ml sample of rumen fluid, drop it into a preservative, and directly extract DNA. And that may not sound exciting to many or all of you, but from a processing point of view and from the ability to really screen animals, that's really exciting for us. And I'll just finish off with the rumen stuff by saying that we actually have a Global Research Alliance project, which is an enteric flagship, and we're taking rumen samples in from all over the world. So from buffalo, from beef cows, from dairy cows that have phenotypes, and we're assimilating that data, and what we're coming up with are predictors and methods that we can then transfer when we're ready in New Zealand, when we have enough samples across the New Zealand dairy cattle industry, that we're ready and we're prepared to put some sort of predictive model in place. So that's the microbial predictor, and as I've said, it's the crux of the matter. But one thing that we
about 6 minutes,
yep.
5 minutes probably, Suzanne.
Okay. So with the methane selection lines, one of the things that we looked at was, okay, so we know that the microbiome in the rumen has changed. We know that the volatile fatty acids are changing. So what does that mean for something like milk? So we took 200 lactating ewes, and we milked them at 2, 4, and 6 weeks post-lambing, and we did it across 2 years. And we looked at their milk composition, we looked at volatile fatty acids in their blood plasma and in their rumen and their rumen microbial profiles. And what we saw was that there's a very, very different fatty acid profile in the low methane sheep than there is in the high methane sheep in her milk. So she has significantly less short-chain fatty acids in her milk. She has significantly more polyunsaturated fatty acids in her milk. And that seems to be driven by the rumen, and the ratio of acetic and butyric acid to propionic and valeric acid is markedly different. So we're looking at sort of tens of percents of difference between these lines, and 30% of the variation being explained by methane line, and 50% of the variation being explained by the microbes. So one of the things that we've also done is look at the offspring in terms of their meat data. We've seen that milk is changing, but if we actually look at meat as a product and the fatty acid profile of meat, so that the green squares in that sort of complicated table are where there are significant differences between the lines, we're seeing the same thing. This is work by Tricia Johnson. So we're seeing that there's a clear change in product, and obviously we need to know that. We may be able to take advantage of this from a screening perspective, but we also want to know what happens when we breed for low methane. And in order to really understand what's going on, we're using, again, global networks to bring together methods and protocol to see how we can develop predictors in milk and meat. So this is my final slide. And the way I sort of see and this is an opinion slide, so yeah, the opinions are all mine. So my proposal for the NZ cattle industry is that the bulls are being measured. We're using green feed devices. I'm sure there'll be some sort of validation with respiration chambers, but I really feel that, and would urge us that we take the other samples, we take rumen profiles, we take blood, we make sure that we have genomic profiles, and that, as Lorna says, we really want to screen the wider population. In terms of the short-term direct measures, we're currently developing pack chambers for calves. We've used pack chambers really successfully in sheep. They've been transported to Norway and used in much bigger sheep. We've used them in goats, and we're now scaling them by volume to measure calves. And we're really hopeful that that will give us the ability to measure sort of 50 calves a day. Genomic profiles is obviously something that the bull companies will be investigating. Rumen microbial profiles, I think, is huge promise, and in particular the milk profiles. If we can do this two ways, what we could do is basically go out now and screen the dairy industry for the milk fingerprint, see if we can find the fingerprints that we're seeing in the high and low sheep, take those animals, bring them back and measure them for methane and see if they differ. So we could turn the whole thing on its head and say, well, we know what the milk from a low methane animal looks like, we think, let's test it in cattle. So there are various ways that we can really start to screen the thousands of cattle that we're going to need to sort of validate those bulls and select those bulls going forward. So I think we're in a really exciting space for the cattle industry, and they're starting with a few of the answers, which is really exciting. So I'll leave it there, and just thank the many people that have worked on this and of course contributed hard-earned funding. So thanks, Jeremy. Thank
you, Suzanne. That was fascinating. Chairman's privilege, I suppose. I'm going to throw you the first question now, and actually to you as well, Lorna. Whereas are we seeing a decrease in fat yield in those milks, or have you not got enough data? The reason I asked that is it's only a couple of years ago that the fat was selling at twice the value of protein out in the global markets, which was an inversion of what had happened for many years. And I think quite a change in the perception of dairy fat and also the product mixes it's put into. So any comments on that aspect? Do we know what it does to fat yield?
So in sheep, we saw no difference at all in the fat yield of the sample. So we've got several hundred samples, and yeah, we've got 1,200 samples in actual fact, and we saw no differences between the lines in the actual, fat composition. Fat percentage, only in the composition.
Yeah, that's great. That was my understanding. And the next thing, of course, is whilst some of those profiles could be easily argued to be sort of healthier fat profiles, certainly from literature, are we confident about the processability of those milks into milk fat products? Again, Suzanne or Lorna, from what you're thinking.
I mean, looking at it from a human consumption point of view, the profiles, as you say, literature-based, look great. If I was making cheese, I'd be a bit more concerned. But really, I think it warrants, investigating and following, and the selection lines are great for kind of continually pushing that envelope. Yeah,
so I think when we're doing the breeding, being very, very conscious of the products that we make in New Zealand from our milks is a critical part of this. So thank you for that. Now I'm going to move to the questions. I've got one here which is right up there. Flavor profiles of the meat and milk. Have we got some evidence for that? Again, Suzanne and Lorna, if you want to chirp in.
We've looked at the meat, and the meat's good. So we've got more branched chain fatty acids. So it's positive. I have no idea for the milk at all.
Mm-hmm. More unsaturated fatty acids can potentially lead to more of an oxidative potential as well in milk. So there's one that's really, there's a whole series of questions around the measurement of methane, if I may. So again, perhaps starting with Lorna, why have we chosen the systems that we have? Why have we not looked at alternatives? You know, a modified ZE, the strengths of green feeds. Why have we been making the measurements the way we have? I think, Suzanne, you answered some of that in your presentation, but starting with Lorna.
Yep, so the ZE is definitely an option, but it's pretty early stage as far as I'm aware. I think there might be some coming out for testing later this year, so clearly wasn't really an option for us in terms of planning. We felt like for what we were doing in terms of repeatable and practical, the green feed ticks boxes, but in terms of phenotyping animals on farm when we're not trying to measure intake at the same time. So if we can get a whole lot of bulls that we do kind of more gold standard measurements on, and then we can measure the daughters, say in a pack chamber where we don't do the intake as well, then that would be great. And there's going to be a whole lot of options that we can explore for that. We're just starting to think about it, and Suzanne doing work in the calf pack is really going to make that easier, because we could take that on farm, take it round sire proving scheme farmers. Yeah, it really makes it a whole lot more practical to get those measurements, but we really want the high quality, precise data, and that's why we've selected what we have. As technology changes, there could be other options come along.
Thank you. There's one here for you, Suzanne. In the past, at AgResearch, the repeatability of methane measurements made over longer intervals, in brackets months, on individual animals, sheep and cows, was quite low. Has this changed?
It's reasonable. It's sort of 0.4 to 0.5. I wouldn't call that particularly low. It's why we measured twice. We are currently in the process of moving to a single measure based on the 5,000 commercial measures we took last year. So you're absolutely right. Methane is very repeatable 2 days in a row. But then when we take it across years, it's less repeatable. And what we're seeing there is the difference between, you know, a feed-driven correlation and something that's stood the test of time and is actually genetic and heritable. So I'm reasonably happy with the repeatabilities. I guess we could argue what a low repeatability is.
Okay, thank you. And sort of building on that, how do we see precision technologies and farming systems in the picture in the future, right? So there's a lot of development going on, collars and these sort of things. What data capture and so on around feed health. How do we see that fitting into the future of both helping with enhance, I suppose, the breeding values that we might determine, but also, if you want, ongoing measurements to look at the productivity of methane as well as the productivity of milk?
Yeah, I mean, I think obviously the digital agriculture space is going to be, you know, really important. We're already putting accelerometers on the high and low methane animals to see if we can gauge feed intake or behavioural patterns at pasture. And I'm sure there are many more digital phenotypes that we will use. Lorna might have more to say on the cow side.
Yeah, please leap in, Lorna.
Yeah, there's lots of potential, especially if we could get that elusive, reasonable estimation of intake at pasture, because that really holds us back with research across a whole lot of spheres. And I guess understanding how much animals are moving, like we've got some GPS collars on cows for different projects, all of that, but also making sure that when we're gathering all this data that we're presenting it back to farmers in a way that they can use to make decisions, because just screeds of data isn't very helpful as a farmer.
Okay, thank you. There's one here on, so you actually presented, Suzanne, some exciting results on the changes in the microbiome that had occurred. Why can't we just transfer those microbiomes from the low emitters to the high emitters? I think you talked something about the morphology of the rumens also changed. Do you want to talk about the relative contributions of those things? You did give us a bit of a graph on that as well.
Yes, so the microbiome certainly seem to be driving a lot of the variance of the traits, and they certainly seem to be underpinning. In terms of transferring from one to another, I think the general evidence is that if you transfer a microbiome from one animal to another, that it will revert. Remember that we're seeing host control of these microbiomes, so it's heritable. So that would infer that it's a quality of the host driving the microbiome. So it may be something to do with the physiological makeup of the animal. And there's much work that could be done in the area on inoculating with other microbiomes, but my gut instinct is that it would need to be done fairly often. So I don't think you would make permanent changes, but yeah, the jury's out on that.
And just as an extension to that, we are talking about the rumen microbiome.
Yes.
And not the further down the digestive tract.
No, the fecal microbiome isn't highly correlated with the rumen microbiome in the ruminant. Different in humans and monogastrics, but.
So let me just. So we've one here. Perhaps it's to you because we're starting with the average flock. So the data presented are based on differences in the high and low methane lines. That was the 11% difference that you clearly showed. Do you know the difference between the low line and the current average flock?
Yeah, so it's around about 6%. So the 6 to 7%, the lows are slightly lower than average compared to the highs. And the variation that we're seeing in commercial flocks is roughly plus or minus a gram per day in methane.
Thank you. Yeah. Sorry, carry on.
What we're hoping for to see across the national flock, if selection was to be put in place, would be something like a 0.5 to 1% decrease in methane per year across the national flock.
And again, keeping going, how many generations of breeding do you think are going to be required to produce the variation from the mean in your low and high methane flocks?
I'm not quite sure I understand the question.
So how many generations of breeding were required? Yeah. So you showed your results. Mm-hmm. How long did it take you to get that 11%?
So around about 2.5, 2.5 to we're approaching the third generation at the moment so far.
Okay, thank you. Just lots of things, comments about great presentations, Lorna and Suzanne. We've got some people answering questions as well, which makes for fun reading. So again, for both of you, I'll read it literally. Is it your hope that you can assays can be used to create a farm emissions profile or just selection?
I think the hope would be that these breeding values are a characteristic of the on-farm calculators that they're programmed in. So as when someone has an environmental plan, the status of their stock is incorporated in their environmental plan, so that they get some credit if they do breed for low methane animals.
Thank you. Anything to add, Lorna?
Yeah, we would see if we can get to that level that it could feed into an overseer or whatever. So when your farm emissions are calculated, and if you're having to pay a carbon tax, then that's credited through.
And Suzanne, just a quick one. In your microbiome profiling, I've got an additional question myself is on this as well. 16S or 18S?
So we're using sequence-based, so we're not using either.
Yeah.
We're actually direct sequencing, so we use a restriction enzyme. We take about 1% of the sequence. So rather than just restrict ourselves to a marker gene, we're taking a much larger amount of sequence data.
So not whole genome sequencing, but significant sequencing.
Yeah, whole genome is wasteful for this. Yeah. So we've sort of come to an optimal then.
Thank you. So I think you've answered the milk protein and fat yield question. So you didn't see differences in either, or did you? Did you see an increase in milk protein? My
No, we didn't. Probably the one thing that we did see that I didn't mention, which is of interest to the dairy industry, is that the low methane animals had a higher somatic cell count. There was no infection, but they just seemed to naturally have a level of somatic cell count that was higher. So whether that's something to do with an immune response, or I don't know. But that again is something that, you know, if you were going to benchmark, that would need to be looked at.
Okay, you mentioned that they've got a higher surface area, so smaller rumen, but equivalent surface area, was it? Yeah. Or was it actually higher?
No, roughly it works out at roughly the same.
Okay, thank you. Okay, I'll ask the last one. Do you think that the influences on fatty acids composition is going to outweigh diet? So the genetic influences you're seeing? No,
I don't. I think diet is still going to be a massive driver. I think, you know, we incorporate in conjunction, and we may well see that these animals use diet in a different way, but I can't imagine that they would ever overwhelm the dietary effects.
Okay, thank you. Look, and I really appreciate Lorna and Suzanne, you sharing those insights with us today. We've got a few other questions. I think you answered some of these during the course of the presentation, but we'll go back and check as well. Anything that we haven't answered, as I said, we will put up on the website to make sure that we are covering everything. We're just about out of time, but I'm really grateful for the work you're doing and appreciate the AgRC